Welcome to Study Loop.
This is the answer to Chapter 22, Problem number 3 from the Smith Organic Chemistry textbook. And this problem asks, how do the following experimental results support the resonance description of the relative stability of acid chlorides compared to amides? The CCl bond length and CH3Cl, and methyl chloride and the comparable acyl chloride are identical at 178 ppm, but the carbon-nitrogen bond in formamide is shorter than the carbon-nitrogen bond in methylamine. So this is sort of a confusingly worded question, but basically, in order to get the answer and kind of see what they're talking about, we're going to need to draw the resonance structures of each of these carbonyl compounds. Starting with the acid chloride here, the resonance structure is going to look like this. So a lone pair from the chlorine can add in to form a double bond, and one of the double bonds between the carbon and oxygen can break. And so we will have a resonance structure that looks like this, where the oxygen has a negative charge and the chlorine has a positive charge. So that would be our major resonance structure there. And then we can do the same thing for the amide here. And it's going to go the same way. So the lone pair on the nitrogen will add in. One of the carbon-oxygen double bonds will break. And so we'll get a very similar looking resonance structure where we now have a carbon-nitrogen double bond. And the nitrogen will have a plus charge. And once again, the oxygen will have 3 lone pairs and a negative charge. So the main point here is that when we're looking at the acid chloride, this resonance structure contributes very little. So this resonance structure for the acid chloride contributes very little to the resonance hybrid. And the reason for that is that chlorine or chloride ion is a weak base. It's a very weak base. And so since it's such a weak base, it's not super eager to donate one of those lone pairs and form this resonance structure. And so a result of that is that there is very little carbon-chlorine double bond character. So very little C double bond Cl character. Okay. However, when we look at the amide, NH2 minus is a strong base, or at least let's say a stronger base. So NH2 minus is a stronger base. And so because of that, we can say it contributes more significantly to the hybrid. So it contributes significantly to hybrid. And so as a result of that, the carbon-nitrogen bond in this molecule the carbon-nitrogen bond in this molecule has more double bond character. Okay, and so it has more double bond character. Double bonds are shorter than single bonds, and so that explains why this carbon-nitrogen bond is shorter than the carbon-nitrogen bond in methylamine. Okay, and so that's the answer here. Again, we got there by drawing resonance structures for each of our carbonyl compounds and considering how much those resonance structures would contribute to each resonance hybrid. And in the case of the amide, it's a pretty significant contribution to the resonance hybrid. And so the carbon-nitrogen bond has more double bond character than the carbon-chlorine bond in the acid chloride. And so, since it has significant double bond character, it is shorter, like a double bond would be. And that's the answer to chapter 22, problem number 3.